Hello, magandang umaga o magandang hapon. We will be discussing today the mass of a solid as a triple integral in rectangular coordinates. Okay. So first, let's motivate what we want to do, and we motivate it by looking at what we've already done. So, bakit three integrals? Ano ba yung two integrals? Siyempre, alam natin yung one integral gives you the area. Yung two integrals, madaming ibig sabihin. One of them is the volume of the solid bounded above by the surface. Okay? And another more interesting for us for this lesson, the more interesting application of double integrals would be the density of a lamina R. So a lamina is just a fancy name for a two-dimensional object, two-dimensional surface. So if f of xy is the density at any point xy of the region R, then the mass of that region is nothing but the double integral of that density function over the region R. So when you want the mass here of a two-dimensional object, now if you want to extend this to find the mass of a three-dimensional object, such as any solid, then we are transcending dimensions. Now, instead of looking at a two-dimensional object, we now look at a three-dimensional object, and therefore, we have to add another integral sign if we want to find the mass of a solid. Of course, we have the same thing here. We have the same integrand. Here, we will just replace f of xy by f of xyz because we're now in three dimensions, and this will still be defined. This will still define the density of the solid at any point xyz. Let's go to the next slide. So before we go to the more complex solids, let's look at the simple rectangular box. So the rectangular box is nothing but the triple integral of three intervals a, b, c, d, r, s. So here, AB is the interval on the x-axis, CD is the interval on the y-axis, and RS is the interval on the z-axis. And you do your drawing techniques, and after combining these intervals, you should get a box of this form, right? So for instance, what is the unit box? The unit box would be 0, 1, 0, 1, 0, 1 cross 0, 1 cross 0, 1. So it will be 0, 1 cube, okay? And the 0, 0, 1 cube is just this box, where this is 0, 1. I mean, so this is 0, 1, 0, 1, 0, 1, 0, 1. That's the unit box, okay? So, but we don't have to restrict ourselves to the unit box. We could be more general. So in general, it's just AB cross CD cross RS. Or you can say it's a collection of all triples XYZ such that X is between A and B, Y is between C and D, and Z is between R and S. And now we are given that the density at any point xyz is f of xyz. So there's a function here that defines the density at any point on the solid. So what we want to do is to find the mass of G. Now, this would be very simple if that density function were a constant. So, if this is a constant, no, kunyari ito ay equal sa C, then the mass by the physics formula is just equal to the density times density times the volume. And in this case, it will be C times, what is the volume of this? The volume will be B minus A D minus C, wala akong space, times S minus R, right? Because the volume of a rectangular solid is nothing but length times width times height. And the formula for mass is density times volume. The problem really is, what if the density function is not a constant? So what if the solid is heterogeneous in terms of density? That means that it means that on this part it could be heavier than this part. And so you cannot just apply this formula because this formula assumes that the density is constant. So this really is a recurring problem in calculus. You want to compute something, and that something, one of the components of the formula of that something is not a constant, but rather it's a function. So what we do is to what do we do before? We partition, no? We partition that thing so that when we go into an infinitesimal part or particle of that thing, we can assume that at that small particle the density is constant, right? Right? So, kunyari is isang I don't know, isang ano bang solid na iba-iba yung density. Kunyari, uh, eraser, 'di ba? May part doon na parang kahoy, may part na medyo soft. So, iba-iba yung density, right? But if you break the eraser down to very small parts, then you can just assume that the density of that very small box, if after partitioning, would be constant. Let's go to the next slide and let's make the partitioning formal. So how do you partition a box? So you can partition a box by partitioning the intervals defining the box. So on the x-axis, you partition AB and so on. So on the z-axis, you partition RS. So you partition them into L, M, and N. And suppose that big N is the number of subboxes that you get. And then you have the subbox Bijk, which is just the cross product of three arbitrary subpartitions. Now, this is what I've been talking about. After partitioning, you get very small particles after. And when you focus on this small particle, the heterogeneity vanishes. Parang dahil maliit na siya, parang pareho na yung density ng particle throughout the particle. And actually, this is because of the inherent assumption that the density is continuous. No, dahil continuous siya, then when you go to the next particle, you don't change so much. Okay, so the volume is not very hard to find. So the volume is just, again, because the partition is another subbox, this the length, width, and the height, and the delta x is defined to be the length of this. So this is just the difference of this and this, right? So when you have kunyari x, y, the length would be y minus x. So delta x is just xi minus 1, and so on. So delta V, which is the volume of the subbox, is nothing but the product of delta X and delta Y and delta Z. Okay, so let's go to the next slide. So let's renumber the subboxes. So this is what I was talking about. Let big N be the number of boxes. Okay, and then how do you make it more formal? The concept that at the small particle the density is constant. So on the small particle, you choose any point, no, any point x star, y star, z star, sub L, in each B sub L, no, which is the subbox L subbox, and assume that BL has a constant density. So the density will just be the function evaluated at that arbitrary point of that subbox. Okay, it follows that the mass of BL, because now you're assuming that this is constant, then your physics laws now apply. So it's equal to the density times volume. And then what do you do after? This is just the mass of the subbox, a very small subbox. So how do you approximate the mass of the whole solid? So it's nothing but you just have to take the sum, no? The sum of all the volumes where L ranges from 1 to n. Remember that n is the number of subboxes. Okay? So now what is the next thing to do? We have a coarse approximation because the partitioning may not be as small as we want. So what we want is that the subboxes will have volumes that will approach to 0. Okay? we define the partition norm of P as the longest diagonal of each subbox. So remember that when you have a subbox, paano na nga ito? Ano ang longest diagonal niya? Ang longest diagonal niya would be square root of x squared plus y squared plus z squared, right? So if this goes to 0, then x and y and z also approaches 0. So when you say that this norm of the partition goes to 0, you're not only making one dimension go to 0, but in fact you're making the three dimensions, the length, the width, and the height, go to 0 as well. Okay, so this is now the final form of the mass. So again, this is just the coarse approximation of the mass, given that you have partitioned the mass into small subboxes. And then, as you take the limit as the partition goes to 0, the norm of the partition goes to 0, then the approximation becomes better and better. And as soon as you take the limit, then the approximation, the limit becomes the true volume, the true mass of the solid. Okay, so we define this more formally. The triple integral of f of x, y, z over the rectangular solid G is defined as this. Okay, so remember again that the norm of the partition actually depends on x, y, and z, and therefore it's but natural to denote it with three integrals. No, the three integrals will denote the integral over x, the integral over y, and the integral over z. Now, if this limit exists, then we say that f is integrable over g. In the next slide, we will look at concrete examples of evaluating triple integrals, as well as some properties of these triple integrals. So see you again in the next part of this lecture.